Okay, let's do 11.5 today. So first thing I want to do is I want to sum up what we've done so far, so then you can get them all. Okay, so a recap. If you got a summation, n equals 1 to infinity of an, okay? First thing you need to know, first thing to look at is if an's do not go to 0, it diverges. If an's do go to 0, then you don't know what happens. Second thing, if you got the summation and the summation, the an's, you got, let's see which one to do first. If you got a r to the n, that goes to the first term over 1 minus the ratio if the absolute value of r is less than 1. Okay? If absolute value of r is bigger than or equal to 1, it diverges. Third thing is if you got the p series, you got 1 over n to the p. If this converges, if what? P is bigger than 1. And if p is less than or equal to 1, it diverges. If p is less than or equal to 1. Okay, now, fourth one is if we've got, you've got this sequence, so you've got a sequence, n equals 1 to infinity of an. And if you can find, you can go put that on all these two. If you can find a function, f of x, and that function is continuous, decreasing, positive, and the function matches your sequence pieces at each one of the integers, then the sequence does exactly the same thing as the integral from 1 to infinity of f of x dx. Okay, so if you got a series, if you can find a function that matches the series, and that function is continuous, decreasing, and positive, then if this integral converges, that series converges. If this integral diverges, that series diverges. And then we got a couple more. So the fifth one we had, and we'll start back at the top. I'll put it down here. The fifth one, if you've got two sequences that are positive, and you know that an is less than bn for all n's, then you know that the sum of an is less than or equal to here, then the sum is less than or equal to the sum of this series of an's, a series of bn's. So if I got a sequence, a positive, and this sequence is always bigger than that sequence, then this sum is always less than that sum. Now, you know something, if you know that this guy blows up, then that guy has to blow up. If you know that this guy converges, then that guy has to converge. And that's the comparison test. And the last one we've done was a limit comparison test. And there, so that's number 6, same type thing. If you got two sequences that are bigger than 0, and if you got the limit as n goes to infinity, one guy over the other one, doesn't matter which one you put on top, usually write a bn over an. If that approaches some number, if that converges some number bigger than 0, then the sum of an and the sum of bn do the same thing. So if an blows up, then that one blows up. If an converges, then that guy converges. And you got to know on these two, the comparison test and the limit comparison test, you got to know something about one of these sums. So you're usually given one, and then you pick something to compare it to that you know something about. Okay, so that's all the stuff that we've done so far. Recap. If the n sides don't go to 0, throw it away, you're done. If they do go to 0, well, then you got to work some more. Okay, if it's the geometric series, then you're fine. We actually know what that one goes to. If it's P series, we'll find these are easy to work with. We don't know exactly where they go to. We know if P is bigger than 1, it converges. Then we got what this one, the integral test, is really nice. On the integral test, we can actually get an error estimate too on these guys. And then the 2 limit comparison tests. Okay, that was all the stuff we know about series so far. 2 more things we know. We know how to get some error bounds. So let's look at the error bounds we know how to do so far. So first one, if your sum n equals 1 to infinity, or wherever you want to start, of a n r to the n, we don't need an error bound on this one. We know this guy equals your first term over 1 minus your ratio, and as long as r is less than 1, then it converges this exact number. So we know exactly where that guy goes to. But if we did found a sequence and we used the ratio, the root and whatever the thing is, the integral test, and we used Sn to approximate it, and we came up with a remainder, we know that the remainder is less than the integral from wherever we stopped, the n to infinity of the function f of x ds. Remember, that function's got to match this guy on the integers. It's got to be continuous, decreasing, and positive. Okay, so there's what we know so far. We know 6 different things, and then we know these 2 things. We know exact answers for those, and here we can find an error bound if we use the integral test to show that it converges. Okay, I'm going to stop right there for a second.